Thank you, Luke, for the introduction. It's really my pleasure to be here today. And in this talk, I'm going to showcase how we can use volcanic terrains to infer the evolution of planetary bodies. My research focuses on investigating the surfaces and shallow subsurface of volcanic terrains, specifically the ones that are formed by effusive eruptions, such as lava flow fields, to infer emplacement dynamics and, in the planetary context, also the evolution, thermo-evolution of planetary bodies. And here on the first slide, I'm showing two of my favorite lava flow fields in the solar system. You can see the Holuhraun eruption that took place in Iceland on the upper panel, and then Elysium Planitia, which is located on Mars, in the lower panel. My research is fueled by a combination of remote sensing data sets as well as techniques. I use a lot of imagery data as well as spectral data and radar sounding data. And then I also do a lot of field work, and I'm focusing on developing new technologies specifically for volcanological applications that you can put on a UAS system, so an unoccupied aircraft system, and in the planetary context also to advance planetary exploration. It's important to understand volcanic processes because volcanism is a primary mechanism by which planetary bodies can get rid of their internal heat. And so understanding volcanism provides you an insight into the thermo-evolution of a planet. Eruptions also discharge large amount of pyroclasts, gases, and volatiles into the atmosphere. And so volcanic eruptions, especially the large ones, are affecting the global climate of planetary bodies. And then last but not least, volcanic terrains modify and shape all of our inner planets in the solar system. And that is specifically true for Mars. Mars is dominated by volcanic terrains. However, we know that Mars was very similar to Earth early on in its history, and it had a dramatic change in the history. So we know that Mars early on had a magnetic field. We also know that there was very intense volcanism early on that then turned towards more sporadic volcanic activity. We also know that Mars had stable water on the surface, forming valley networks as well as large outflow channels, and also formed a denser atmosphere compared to today. Today, Mars looks very different. It's rather dry and very cold. And so the question is, what happened? And I think the key to answer that question and to understand the evolution and the history of the planet is by studying volcanic terrains. First of all, there are a couple of reasons. First of all, Mars is dominated by volcanic terrains, making up more than 50% of the entire surface. Secondly, unlike on Earth, where we have erosion, sedimentation, and tectonic that is erasing, mantling, and recycling the record that we would see on the surface, on Mars we have wonderfully exposed and remarkably well-deserved volcanic terrains, and that includes billions of years of geology. So we have very old volcanic terrains, including the largest volcanic terrain, which is called Tharsis, that is outlined here on the left. And Tharsis is also home to the largest volcano in the solar system, which is called Olympus Mons. On the right, you can see the second largest, which is called Elysium Volcanic Province. And then in between, we have Syrtis Major, which is by area the third largest. All of the edifices that are shown here and pointed towards with the arrow are sheared volcanoes. However, Mars is also home to huge flood lavas, so very similar to large igneous provinces we had here on Earth. And these flood lavas include the youngest volcanic terrain we have on the planet, and so there might have been a change in volcanic style, forming sheared volcanoes early on, and then towards fissure-fed eruption, forming flood basalts in the late history. So one of the most commonly questions I get about my research is Mars still volcanically active today? And I think to answer that question, you really want to understand Elysium Planitia, which is the youngest volcanic terrain we have on the planet. Elysium Planitia is located just southeast of Elysium Mons, and it is home to the youngest volcanic terrain, including Athabasca Valles, which you can see here with the red outline. Athabasca Valles is only a few million years old. And that means we have very fresh and almost unmodified surfaces with a high variance of lava morphologies. And these lava morphologies can provide a window into the emplacement dynamics. In addition to the volcanic importance of Elysium Planitia, it's also really important to understand Elysium Planitia from a fluvial history. Elysium Planitia is home to the largest aqueously carved outflow channel in the late Amazonian, likely carved within the last 120 million years, which is called Martyr Valles, and it's located in the south. Now, the interior exploration and using seismic investigation, geology, and heat transport, called InSight, detected more than 1,300 seismic events. The majority of them are actually located in Elysium Planitia. And the seismic character is consistent with melt, so magma, moving still today beneath Elysium Planitia. In addition to the evidence, let's say, the measurements that InSight provided, geophysical investigations also suggest that we have a mantle plume active still beneath Elysium Planitia today. And so studying the recent history in Elysium Planitia provides us an insight into the hydrological, the volcanic, and also magmatic evolution of the planet. I did a study in 2018, and you can see a result here on the left, where I focused on two of the largest flood lavas. And what is shown here as the different color-coded are different lava facies, so different lava morphologies within one geologic unit, specifically here, flood basalt. And so these high variants can tell you something about the emplacement dynamic, and so it's really important to pay attention to the details we see at the surface. As I always like to say, lava morphologies are like open books if you know how to read them. And so my research really focused on how to read lava morphologies, what can we learn about the emplacement dynamics, and really establish a link. The best way to answer that question is to learn from Earth. Earth is a perfect laboratory where you can establish fundamental links and concepts here on Earth and then apply that to other planetary bodies, such as on Mars. And so the first part of my key research area is to characterize and understand volcanic surfaces here on Earth, specifically by determining a link between unsteady eruption conditions associated with fissure-fed eruptions, and then see if there is a link to the final lava morphology, so the solidified lava. Then I'm applying what we have learned here on Earth to other planetary bodies to infer eruption dynamics and magmatic processes, and specifically I'm going to show you an example how I did that in Elysium Planitia, which is the youngest volcanic terrain on Mars. Now, even though Mars is dominated by volcanic processes, Mars also had this turbulent interaction of water modifying the surface, and so part of my Martian work is also to understand and qualify and quantify aqueous processes, as well as lava-water interactions, specifically to assess the habitability of the planet. The last part of my research is to improve UAS technology, specifically expanding UAS capabilities for dedicated volcanological applications during active eruptions, as well as developing concepts and technologies to inform the next generation of planetary missions. So the two most commonly lava types that we have here on Earth are Holuhraun and AA. Holuhraun and AA are amazing because they have very contrasting surface morphologies that can be linked to the different emplacement dynamics. And so Holuhraun is characterized by a rather smooth, coherent crust. Sometimes it creates billows and ropes on the surface. AA, in contrast, is rather rough, and you can see it's more clinkery at the surface. Holuhraun and AA also have a different emplacement dynamic. So Holuhraun is emplaced via tube fed and sheet fed, so that means that the lava has time to build a crust, being very thermally insulating. And that allows for relatively low viscosities, and we are in a low shear strain rate regime. AA, in contrast, is transported via open channels closer to the vent that you can see in the background of the image here, and then via avalanches at the flow front. We have high viscosities and high shear strain rates. Now, I think our observations here on Earth are biased towards Hawaiian volcanism, such as AA and Holuhraun. And that is not representative of what we are seeing on flat basalt eruptions, specifically the ones that we see on Mars. The lava morphologies look very different, and that means that the emplacement dynamics, I think, were different. A reason why I think Hawaiian volcanic materials such as AA and Holuhraun are so commonly described is, well, Hawaii has a very active eruption, active volcano, so researchers love to study Hawaii. And then another reason is that the flat basalts we have here on Earth, such as the Columbia River basalts, are very old. They are the youngest of the large igneous provinces, but they are still 50 million years old. So all of the information that was on the surface is eroded away or buried. Now, the largest eruption during human times was the Lucky eruption in Iceland 250 years ago. Even though that was well documented during the time, 250 years ago, we didn't really have the ability to measure active eruptions. And so there was a huge gap in understanding large fissure-fed eruptions here on Earth. That has changed dramatically with the 2014-2015 Holuhraun eruption in Iceland. And here I'm showing you an overfly. The Holuhraun eruption site is the largest fissure-fed eruption that we had since 250 years. And that provided a really unique opportunity for us to understand large fissure-fed eruptions, and specifically what we can learn about the emplacement dynamics by looking at their surface. So it was a long-lasting eruption. It started in August 2014 and ended in February 2015. And here you are looking towards Bogor, which is the main feeder system, the main vent. And you can see that the vent is quite full with lava, but it was towards the end of the eruption where the effusion rate was rather low. So we are already in a bubbling phase. At the beginning of the eruption, you saw lava fountaining coming out of Bogor. Now, Holuhraun is located in the Icelandic highlands, just north of the Vatnajökull ice cap. It's associated with the Badabunga-Vatnajökull volcanic system, which is marked here in dark red. It was very likely sourced from the Badabunga central volcano, which is sitting underneath the Vatnajökull ice cap. And the great reason why Holuhraun is so unique to understand controlling parameters of lava morphologies is because of a couple of reasons. First of all, the lava flow was emplaced on a very flat-lying glacial outwash plain, and that means the topography didn't affect the lava morphology. In addition to that, the chemistry remained constant, and so the chemistry also didn't affect the lava morphologies. And we know that topography and chemistry are really parameters that can affect the lava morphologies. At Holuhraun, that wasn't the case, and that is why we specifically can correlate that or link that to effusion rates and test if effusion rate is controlling lava morphologies. Now, Holuhraun is also an amazing analog site for young volcanic terrains we have on Mars, and that is due to a couple of reasons. First of all, the geologic setting is very similar. In Iceland, the high volcanic rates that we have is due to the fact that we are sitting at a divergent plate boundary, and we also have a mantle plume upwelling beneath the land masses in Iceland. In Elysium Planitia, even though we do not have plate tectonics, we are in an extensional setting, which is evidenced by the largest and youngest fissure system on the planet, which is called Cerberus Plains. And we also have a mantle plume beneath the plains. So there's still many debates about how to produce melt currently beneath Elysium Planitia. One model is trying to address that by convection models. The other one is arguing it's because of a thick lithosphere that is insulating, allowing to produce melt. However, it doesn't really matter what produces the melt. Once the melt reaches the surface, it creates fissure-fed eruptions, forming basaltic lava flow fields. And that is exactly the same volcanic style and the same rock type we are seeing in Iceland at the Holuhraun eruption. And more importantly, it forms the same morphologies that we are seeing. At Holuhraun here on the left-hand side, you can see an example in the bluish color. And then next to it, I'm showing an example in Elysium Planitia in the grayish color. Okay, now I'm showing you one of the results of the work of the characterization of the Holuhraun lava flow field. So that is a facies map, and one of the main findings is that Holuhraun is dominated by transitional lava types. We do not see the end members AA and Pohjola. Instead, we have rubbly lava in place, dominating by 60% of the entire lava flow field. It's shown here with a brown color. And the surface characteristic looks very similar to AA. It's a highly disrupted lava surface. However, the emplacement dynamics is a little bit different. I'm going to talk about that in a minute. And the second most common is spiny, which is a more continuous lava surface. It's rather smooth and is shown here in the red color. So I did that facies map based on remote sensing data, very equal to the ones we have on Mars. So the highest resolution data set we have on Mars are about 25 centimeters per pixel. The remote sensing data that I that the facies map is based on is 20 centimeters per pixel. And then I went into the field, did a lot of field work, and while doing that, I used UAS systems to get higher resolution ortho images to better characterize the emplacement dynamics and the surface characteristics, but also to investigate what informations are lost depending on if you work with remote sensing data equivalent to the ones we have on Mars versus higher resolution images. And here I'm showing a couple of drones that I was using. So that is now Burger, a year after the eruption stopped. You can see it's still a little bit outgassing at the vent. And you can see that the lava now has drained, so that is the same vent that I showed you a couple of minutes ago when it was filled with lava. You can also see me standing here at the rim of the vent, piloting the drone through the vent. And I also used a lot of summers to ground truth the facies map that I was doing. And so this summer was actually the first summer I haven't been into the field since 2015. And yeah, so I had a lot of wet and cold summers during my recent years. Now the cool thing is, combined with even higher resolution orthomosaics that you can see here that we got from the drones and due to terrain models, I was finally able to put out the facies map and also reconstruct how we think the lava was in place. So first of all, you have the emplacement of the lava, you form a nice crust because it's cooling, and then you have a disruption event that can be caused by surges at the vent. That is forming slabs, so the crust is breaking apart, forming slabby lava. With episodic disruption, you continue to break apart the slabs into rubble, forming a disrupted lava crust. However, the important thing is, after that, you form a secondary crust insulating the molten core, and that allows the lava to be insulated, and so it can contain its heat, and that is very important for large lava flow emplacement, especially the ones on Mars where you expect that the lava is losing quite some heat, especially when we talk about 2,000 kilometer long lavas. You would expect that they stall beforehand and cannot emplace over these distances. I think the answer to that question is that we actually don't see on Mars, even though it looks very similar to rubbly. I think we see rubbly on lava, on Mars. And rubbly allows for inflation, which is something we see at Voigt as well. Now, then, after the inflation, you create spiny lava. That's the second most common one. And that can be caused by breakouts. So the still molten core can break out of the rubble, for example, when you have surges of lava in the pathway. All right, so now I think the really cool thing is that now that we have the facies map and we have characterized the entire lava flow view, we can now use time-average discharge rate, which is a type of effusion rate you can get from remote sensing data, to see if there is a correlation between the lava facies and the effusion rate. So I did that by creating first a chronological map. So I used all the data we had available, including a GPS in situ measurements during the eruption, but then also satellite images that included radar imagery, thermal, and airplane data. One of the findings is that the eruption can be grouped into 3 phases where one facies dominates. In the beginning of the eruption, you had rubbly that was emplaced. Towards the middle of the eruption, you had undifferentiated rubbly spiny, which is a hybrid between rubbly and spiny. And then towards the end of the eruption, spiny dominated. Now, I also showed that there is indeed a correlation between the final lava morphologies and the effusion rates. And so there is a strong correlation between rubble emplacement and time-average discharge rate, and a strong anti-correlation between spiny and time-average discharge rate, which means if you have high lava effusion rates and a high pulsating at the vent, so high disruption events, you create rubble. When you have a low effusion rate and a more continuous lava supply, you create spiny. I was also interested in seeing how time-average discharge rate, which you can get from remote sensing data, is correlated with local effusion rates. And what I have found is that in the beginning, when the lava flow field is rather simple, let's say you have one feeding system, such as one lava channel, the time-average discharge rate is a really good proxy for the local effusion rate. However, with the time and the lava flow field becomes more complicated, and that is what I'm showing here, when you have multiple active feeding systems, such as the 3 lava channels we are seeing that are simultaneously active. During that time, the time-average discharge rate is not a good proxy for the local effusion rate. So what did Holuhraun teach us? So first of all, Holuhraun is dominated by transitional lava types, rubbly and spiny, and not by the traditional lava types that are so commonly described here on Earth and Voigt. And that is important because even though rubbly looks very similar to remote sensing data, it has a different emplacement regime, specifically being the fact that you're not losing a lot of heat, you're thermally insulating your pathway, allowing for longer distances. It's also important to pay attention to these details when you want to do lava flow and placement models. Last but not least, I have shown that if you have high effusion rates and high pulsating at lava band, you form rubble, and in contrast, when you have low effusion rate and a more continuous lava supply, you form spiny. Now we can take what I have learned on Earth, specifically at Holuhraun, to apply that to Mars. To constrain the late-stage volcanism and the thermal state that Mars is in today, we really have to understand the youngest volcanic terrain, which is Elysium Planitia. And there have been many open questions, very simple ones, such as what are the materials that are making up the plants? Do we see ice, sediment, or lava? There have been a long-standing debate that in Elysium Planitia, the materials are actually looking like ice. And there was a very recent paper saying that this huge valley system, Monte Valles, is filled with ice still today. I think that's not what we are seeing. From a volcanological point of view, I was really interested in seeing how many eruptions did we have, what was the timing and the flux of these eruptions. And also, where were they fed from, because all of that can give you an insight if there was a change in volcanic activity during the late stage volcanic activity on Mars. From a fluvial activity point of view, we really want to understand how much erosion happened. We are talking about a valley that is longer than 2,000 kilometers. So eroding a valley of 2,000 kilometers would need a lot of water. And we are talking about very relatively young ages, so 125 million years, where we typically don't expect to have water stable at the surface, considering that we are equatorial here in Elysium Planitia. So to address many of these questions, not all yet, I started doing small pieces, and in 2018 I specifically did a localized study focusing on two of the largest ones, Rahivalis and Mativalis, doing a localized study very detailed into lava facies. What I found is that Rahivalis can be explained by flood volcanism, and that is interesting because there have been studies suggesting that Rahivalis is actually home to eskers, which are glacial features. Now, I was also able to constrain the surface age. Rahivalis is 20 million years old, and that is an order of magnitude younger than previously suggested, which I think makes the glacial hypothesis even less likely, especially since we can explain these senior ridges with flat basalt eruptions. Now, Mativalis is much younger, 9 million years, and Mativalis is amazing because it's one of the youngest, and so we see a huge variety of different lava morphologies. And so Mativalis really taught me how flat basalts look like. Now at that point I wasn't really able to detangle the entire volcanic history because it's so hard to tell apart where the different eruptions are, where the different lava flow margins are. That changed with Holuhraun. With Holuhraun I really got a good understanding of what the lava morphologies teach you about the emplacement dynamics and where the flow margins are, even though if they are partially mantled by aeolian materia. And so then I was like, okay, let's do that. Let's look at all the lava flow fields from the surface and the subsurface to reconstruct the entire volcanic evolution. I did that by a multifaceted approach from 2D to 3D, where I looked at the surface to characterize the variety of different morphologies, but also to address the origin of the materials, to map out the unit extensions, so the area as well as the unit relationships. And then use Charade, which is the Mars shallow radar sounder, to determine the material properties, the origin, the thickness of the unit, to get a volume combined with the area, and also the unit relationships. Here on the right-hand side, you can see one of my mapping findings. And Elysium Planitia is huge. It's even larger than Texas. It's making up 1% of the entire Martian surface. And I have found that, generally speaking, Elysium Planitia is composed of 5 main flow units, though it's a little bit more complicated than that, especially in the central part that I'm going to show you in a minute. And then, in addition, we also have 19 lava shields. I also want to point out that we do have volcanic rootless cones. They are marked with blue dots, a little bit hard to see, in Athabasca-Valles, and Mativalis and Gotcha-Valles. Volcanic rootless cones are formed by volcanic activity when lava interacts with volatiles in the subsurface. So that can mean that there was water present at the time of the eruption or icy sediments. And that is really interesting, especially since we see it in Athabasca-Valles, which is only 1 million years old. So our current understanding is that water should not be present during that time. Now the central part is a little bit more complicated, so I used a higher digitizing scale and was able to separate out 21 separate lava flow fields in addition to the 19 lava shields, which means we have 40 different eruptions making up Elysium Planitia. And their morphology, the vent characteristics, where they were fed from, as well as the volume, are pointing towards a different volcanic style. The subsurface mapping, I looked through more than 2,000 radiograms, digitized almost 2,000 reflectors, and I want to bring your attention to a couple of things. So here are very typical radiograms from the different flood lavas. I want to point out that they are a couple of units where we see multiple stacked reflectors, meaning that we had multiple episodes of volcanic eruptions. And that is true in Rahivalis, where you can see a stacked reflector, as well as in Mativalis, where we see up to 3 stacked reflectors. It's also really nice that you can see the stratigraphic relationship between these flat basalts in Sharat. And you can see that in Rahivalis, where Mativalis is sitting out on top of Rahivalis, and the same is true for Sebel's plains and Mativalis. Now, coming back to the very simple question, what are the plains made of? Well, is it ice or is it lava? All of my surface characterizations are consistent with flat basalts. I do not see any evidence of ice materials, morphologies. And the same is true for the subsurface characterization. We got a permittivity of 7.8 plus minus 1, which is very consistent with basaltic lava flows we have on Mars. That is also proven by the Perseverance rover, which has a ground penetrating radar on the rover. As a reminder, ice would be around 3, so everything we are seeing is consistent with lava. Now, the cool thing is that we were now able to reconstruct the entire volcanological history. So in the beginning, we had the emplacement of Gojavalis here in the north, and then Rahivalis. The different color codes represent the depth of the reflectors we are seeing. Cool colors are relatively shallow reflectors. Deep red colors represent deeper reflectors. After that, we had the emplacement of Rahivalis 2, so that's where we see the stacked reflectors. We had 2 different flat basalts emplaced here in the region. The deeper reflector is not exposed to the surface, but our reflectors were so dense that we were actually able to reconstruct the flat basalt, even though it's not exposed to the surface. After that, we had the emplacement of Mativalis, and then the central part in Sebel's plains. And last but not least, in the west, that's the youngest Athabasca-Vallis, and it's also by volume the smallest. However, when I say smallest, we are still talking about huge volume of lava. The smallest is 4,000 cubic kilometers of lava. The largest one is Rahivalis with 60,000 cubic kilometers of lava. Now, we also found interesting findings about results about the aqueous alteration. So since we were able to do a DTM, a pre-eruption DTM, if you want so, we were able to find that Mativalis is much longer than previously thought, actually more than 1,000 kilometers longer, going all the way into the central part. And we were able to reconstruct the paleoflow direction of the water. So we now know that the water was carved up from up here, also likely from a Cerberus plain segment. After that, we had the emplacement of Mativalis, so this huge aqueously carved channel is now buried by lava. We also found that the channel, the previously carved channel, is much shallower than previously thought. So it's longer, but shallower. All right, so in Elysium Planitia, I uncovered 40 different eruptions. Generally speaking, Elysium Planitia is composed of 5 flat basalts and smaller lava sheets, though the central part is actually a little bit more complicated. We found that we had episodic volcanic eruptions resulting in the emplacement of several lava flow fields, and that is very similar to what we are seeing at large aquilinoous provinces here on Earth, such as the Columbia River basalts. That is true for the magnitude, the architecture, and also the volumes we are seeing. And then the pre-eruption DTM exposed the largest valley system in the young history that was aqueously carved, and we were able to reconstruct a paleoflow direction from the northwest to the southeast, and that was then filled by even younger lava flow fields following the same flow direction. Now, in Elysium Planitia, the water-rock interaction was relatively short-lived. However, there are regions on Mars where you have longer water-rock interaction, which is really important to assess the habitability. And so now we are going to one of the oldest volcanic terrains, Syrtis Major, to assess the longevity of water-rock interactions, specifically by looking at hydrated silica. So we're switching a little bit towards geochemistry and spectral analysis. So I addressed the hydrated silica with the spectrometer that we have on Mars, which is called CRISM, and specifically looked for the crystallinity of hydrated silica. And that is important because the crystallinity is a good proxy for the intensity and longevity of water-rock interaction. So generally speaking, you have increasing crystallinity with a increasing water-rock interaction, forming different phases of hydrated silica. So you start with the amorphous phase, opal A, and then you continue to opal C, CT, and microcrystalline quartz with continuous aqueous alteration. Now, in addition to assessing the environmental settings of hydrated silica, it's also really interesting from an astrobiological view because silicic materials, specifically opal A, are really good to record biosignatures. And that is especially true for opal A because with continuous aqueous alteration, you can overprint previously structures, and so the more amorphous phases such as opal A are more important because it's more likely to have the biosignatures. So Syrtis Major is located north of Hellas, west of Syrtis, very close to where Perseverance and Curiosity are located in Jezero crater. Syrtis Major is home to one of the first prominent detections of hydrated silica from orbital near-infrared data. And it's also really unique amongst volcanic terrains because it experienced both explosive as well as effusive volcanism, and that resulted in a variety of different lava deposits, including Holuhraun-rich but also silica-rich lavas, as well as hydrated silica, which is here specifically associated or interpreted to be hydrothermal activities. And that provided a unique opportunity to test our hypothesis that older regions, specifically Noachian age and early Hesperian, should exhibit more crystalline phases of hydrated silica because these materials should have had more time to interact with water. In contrast, younger regions are expected to host less crystalline phases of hydrated silica because here we had limited aqueous alteration. And so I used a combined approach, doing first geological assessment, then spectral assessment. For the geology, I created geologic maps as well as crater size frequency distributions, which allow us to constrain the surface age. And then I used the spectral data to first find hydrated silica and then characterize the crystallinity, specifically by looking at the 1.4. So here on Earth, it has been shown that you have less crystalline phases with shorter wavelengths, specifically looking at the 1.4 absorption band position. And then with more crystalline phases, the 1.4 absorption position moves towards longer wavelengths. So a couple of results. First of all, we were able to group the hydrated silica into 3 different study sites. The northern part showed hydrated silica as well as other hydrated minerals such as FGML, phyllosilicates, kaolinite, as well as mixtures between other minerals, other hydrated minerals and hydrated silicas. And then the central part, where we have 2 caldera systems, we only see hydrated silica. The geologic assessment showed that hydrated silica is associated with 2 different geologic units. The very old one, brownish unit that we call Highlands, with an age of 3.5 and 3.7 billion years. And then that is true for both locations. And then the younger terrains, the purple unit, that is the volcanic terrains. And you can see here an age of 2.5 as well as 2.4 on the southern caldera. And so, let's see. So we are talking about 1 billion years of difference, 2.7 billion years to 2.4 to 3.7 billion years. Now here on the right-hand side, I'm showing you examples how these different spectra look like. The highlands in the upper panel, and then the younger paterates in the lower panel. And if you specifically look at the 1.4 absorption position, you can see there is a change, and so here I'm zooming into that. And what we are seeing is that the younger pateras have shorter wavelength positions, and the older highlands have longer wavelength position. That's exactly what our hypothesis suggested in the beginning. Now, I'm in the process of doing a global assessment, because at the end we don't only want to have a regional understanding of the water availability of Mars, we want to have it globally. And so here I'm using an automated detection combined with a manual inspection, and then I combined that with a global geologic map by Tanaka et al. And so the global automated detection showed that we have hydrated silica in 400 and roughly 50 CRISM images. After the manual inspection, where I specifically looked through the hydrated silica spectral to identify the ones that have very strong 1.4 micron band position, allowing us to do the crystallinity assessment. They are marked here with yellow and red, and they are about 300. Now, our preliminary results show that hydrated silica by number is more abundant in the earlier history, so the Noachian brownish units and early Hesperian units shown here in yellow. And then we also find hydrated silica, which I think was a little bit surprising, in the Amazonian units, so where water is not supposed to be stable at the surface. All right, so for the Syrtis Major finding, we found that hydrated silica is associated with two different geologic units, the young volcanic terrain with an age of 2.4, and then the highland terrain with an age of 3.5. The young volcanic have shorter wavelength positions, suggesting that these younger materials have experienced relatively limited aqueous alteration, so it's likely thermal activity towards the end stage volcanism. We are seeing it in the caldera. And then the highland terrains have longer wavelength position, specifically of the 1.4, indicating that older highlands had more time to interact with water, while also producing other accessory minerals such as hydrated minerals such as phyllosilicates and cryolinites. The global assessment, we found that hydrated silica is spread throughout the entire history of Mars, including all of the periods. However, it is more abundant in the earlier history. That's what we expected. And currently, I'm assessing every single geologic setting of the detection, because the global geologic map doesn't have the resolution we need to actually do the geologic assessment. All right, so the last few minutes I'm going to talk a little bit about how my research is improving technology specifically that can be flown on UAS systems. And so, in an ideal world, we would want to have in situ investigation of young volcanic materials on Mars. However, there are a lot of challenges right now. Specifically, young volcanics are relatively rough, so rovers would not be able to pass them, traverse them. I think the solution to that is using a helicopter, and Ingenuity got us one step closer. Ingenuity was the first ever flown helicopter on a different planet. Now we also have Dragonfly coming out, who is going to fly on Saturn's moon Titan. So it is really important that we pay attention to what instruments we need to investigate young volcanics, and specifically what instruments we can put on a helicopter, but also to investigate and evaluate science operations and investigation concepts. And that is what RAVEN was part of. RAVEN stands for Rover Aerial Vehicle Exploration Network, where I'm the deputy guide. And we took a rover and a bunch of helicopters into the field to test different science operation concepts that are based on a rover only, a helicopter only, and a combined mission concept. In addition to that, we also developed UAS technologies. And here I'm showing you our wonderful field team. We had more than 30 different scientists, engineers, and technologists that we brought into the field throughout a variety of different levels. We had undergraduate students, graduate students, postdocs, professors, senior professors, as well as people who didn't do science. So that was amazing. So a couple of technology demonstrations. We mainly focused on sampling technologies that we can put on a helicopter, such as a drill, 4 different scoop designs, as well as a claw. So here, that is a claw where we are trying to get a sample tube, and the sample tube is to scale compared to the sample tube that Perseverance put on the surface of Mars. And then we also did terrain relative navigation as part of our technology demonstration. Now we also got recently a new P-STAR funded, which is PANTHER, standing for Passive Autonomy Navigation, Topography and Habitability Exploration, where we are going to develop a passive radar, and then we are going to mount it on a UAS system to use it as an altimeter to measure the topography while the drone is flying, and then also use it as a dual frequency radar sounder while the drone is sitting on the floor. And so that is really important, especially when you think about that the atmosphere on Mars is so much thinner. You want to make very smart decisions of what type of instruments you put on a drone, but also you want to have the weight as light as possible. The cool thing about passive is that you don't need a transmitter like an active radar. You only need the antenna. So it's super light, and it's also low in resources when you think about volume and science operations. Now here on Earth, many emplacement dynamic parameters that we would want to have during the eruptions are really hard to get, because you would need to get close to the flowing lava, and that is why I think UAS are so amazing. You can just take out your drone, you can fly it, you can hover it above flowing lava, which means you are safe and you get the information you need. And here I'm giving you an example how I used a drone to get local fusion rate at the Fiaccardai sphere eruption in 2021. So I was just hovering the drone. I was able to calculate the velocities that we can then translate into local fusion rates, and amazingly also compare and correlate to the final lava morphologies that is emplaced at the flow front that is fed by the lava channel. Now, looking towards the future, in Elysium Planitia there's still a lot to do, specifically constraining the timing and flux of volcanism. And so I have a proposal right now in where I want to test the hypothesis that I think is true, where you had a systematic change in volcanic activity during the late Amazonian, going from low volume lava flow fields towards huge volume flat lavas. And I think that is also related to the different storage depth, where you had storage within the crust towards earlier phases, and then the storage went deeper towards the late Amazonian. Now, with the surface and subsurface observation and measurements, for example, the eruption locations, the volumes, and the timing, we can also use now our observational constraints to validate 3D convection models, and thereby constraining parameters for the magmatic evolution. So specifically showing us, trying to get a melt in the melt production models globally on Mars, where we see eruptions at the surface during the time that we see them erupt. So thereby specifically really constraining the parameter space to get these melts where we need them at the surface. I also got an MDEP funded, where I'm looking at Amazonas Planitia, which is also a very young volcanic plain. And here, again, very simple questions we don't know. Is it ice, sediment, or lava we are seeing? And that was fueled by a very recent impactor that happened on Mars that exposed ice today at the surface, and that happened in 2021. So the question is why? That is shown here. We also see very young fissure system sitting in a polar part basin. So the question here is, what is the tectonic influence of these lava flow fields that we see emerging from the chains that you are seeing here in the upper panel, as well as we see features that might be fluvial channels. So this project is funded, and the approach is to, again, do a surface characterization and then combine that with subsurface observation, and I think that is a project that is perfect for graduate students. It's fully funded, and I'm really excited to get started on that. And with that, I will leave you with one of my favorite videos of the Fiagrada's eruption, where I was really lucky because we were doing our drone observations, and then 10 meters next to me there was a new fissure opening. And so that was pretty amazing because I have never seen that before. So we were able to monitor fissure opening, and we were so excited that we just stayed into the night, and that is one of our videos. So with that, I thank you for your attention, and I'm happy to take questions.